and welcome to NPTEL MOOC on fiber optic communication systems and techniques. We will now discuss in this module a different way of conveying information using optical fibers. Of course, this different way of conveying information is quite well known in the other communication systems, especially in the wireless communication system or the older wired copper cable communication system. But what makes it interesting for optical communication system is that unlike the previous method where we modulated information on the intensity of the optical signal, that is, if you wanted to transmit a bit 0, you would transmit a certain power and then you would transmit another power to send a bit 1. Usually the power that is sent for 0 was very small and the power that is sent for 1 depended on what is the maximum limit that the channel can actually withstand. Okay. And as we saw in the previous modules, this type of a simple modulation technique was actually equivalent to an on-off keying system, and at the output of the fiber all you had to do was to place appropriate filters, amplifiers, and then eventually put in a photodetector, follow it up by some simple signal processing in order to retrieve the information that was sent. Okay. So the modulator structure was simple and the receiver structure was also simple, and this was actually very nicely done in the sense that the receiver, which the front end part of the receiver would essentially consist of a photodetector, and we know that photodetectors are going to measure the intensity of the optical signal because the current that they generate will actually be directly proportional to the optical power that is incident on it. Okay. However, this type of a modulation is actually very poor way of utilizing the spectrum. So this is very poor way of spectrum utilization, which means that the spectral efficiency, that is the way in which we are going to use the allotted spectrum, is actually not very good, because at most you are going to send 1 bit per symbol, right? Even if you were to put in, for example, polarization multiplexed system in which you would actually transmit 2 different polarizations, and at the output you actually put 2 sets of photodetectors, retrieve the 2 polarizations separately and then determine the bits, your bit per symbol per polarization would always be equal to 1 bit per symbol. So you could even say that even when I use polarization, I am essentially not making the full utilization of the spectrum, although yes, considering 2 polarizations I would be transmitting 2 bits, but then if you actually look for per bit per symbol per polarization, that would essentially be just equal to 1. Okay. And this is not a new problem, this is an old problem, and people have suggested many methods to increase the number of bits per symbol, and in this case you can increase the number of bits per symbol per polarization. And what are those methods? Those methods fall generally under the headline of what is called as higher order modulation. In the intensity modulation, we sent bit 0 by transmitting 0 here, right, over one time duration, and for sending bit 1 we transmitted the carrier signal with an amplitude of square root ps, or equivalently the baseband signal which has an amplitude of square root ps, and of course this was a duration of 1 bit period or 1 symbol period. Here bit and symbol were actually equal to each other, and this is exactly what we transmitted. Please note that we may have some phase to the carrier, but we did not exploit this phase, nor we exploited the fact that we could actually have modulated omega naught. By the way, I am showing you the amplitude version of the equations, but if you were to just follow the optical power, this would correspond to optical power of 0 watts, and this would correspond to an optical power of ps watts over whatever the time duration that you are actually transmitting, right? So you can also of course write down this ps in terms of energy as well. So you can say that ps is equal to es times t, where t is the duration of the time or time period of 1 bit, and this is what we actually transmitted in terms of the power. But if you go back and look at it in terms of the amplitude, the electric field that would be propagated in the fiber would actually be in this form: exponential to the power j omega naught t plus theta. We neither exploited theta, we exploited omega naught, we just changed the amplitude. Now you could take this forward. For example, one way of implementing this higher order modulation is to consider 4 different amplitude levels. So let us say that this amplitude level is 0, then you have an amplitude level of P1, then you have P2 and P3, with P3 being the maximum power that the link can withstand, and therefore within the minimum power 0 to maximum power P3 that the link can withstand, we have created two sub levels of actually other powers P1 and P2. Now we want to write in terms of amplitude, we don't want to write in terms of power, so therefore I am going to put a square root of this one to everything. And then if you remember our signal space analysis, we said that any signal which has a certain duration and has a certain finite energy could be actually expanded in terms of certain basis functions, right, and that is precisely what we have done here. These S0, S1, S2, S3 are all different symbols or all different waveforms, and each of those waveforms are actually one dimensional signals themselves. They have a point up there. So the ith signal here can be written as square root of Pi with P0 being equal to 0, this is my definition, times phi I of t. So I have a one dimensional signal set here. So all these signals Si of t, which are actually square root of Pi phi 1 of t, where phi 1 is the basis for these functions, and S1, S0, S1, S2 and S3 all are those signals. So this essentially means that these are the constellation points. So any signal Si of t can be put onto a one-to-one correspondence with the appropriate constellation point square root Pi, which is defined in the space phi 1. Of course, I am showing you two-dimensional space, but in reality the signals are actually only on one dimension. Okay. In fact, if you take this phi 1 to be the in-phase component and phi 2 to be the quadrature component, you actually end up with the even more common in-phase quadrature component wise constellation. So in-phase would essentially be cosine omega 0 t and quadrature will be sine omega 0 t. So you can use these to even represent all the signals that we are going to consider from now on in terms of this signal space. We have already done this for the case of on-off keying, where we had only two levels S0 and S1 with appropriate powers of 0 and root P1. Okay, so this is the way in which you can actually extend the simple concept of on-off keying to say multi-level signaling. Okay, so this is multi-level signaling, or simply called as amplitude shift keying, because your amplitude is now going over more than one level. Now what is the advantage of doing this? Now the advantage here is that since at any time t, so since any time t which is a signaling interval, I am about to choose one of the four messages, I can assign binary symbols to these, binary date or binary word to each of these S0, S1, S2 and S3. How? I can code this 0 0 or the 0 amplitude waveform or the symbol S0 as 0 0, then the next amplitude I can consider it to be 0 1, then I have 1 0 and then I have 1 1. Okay. So these are the four different amplitude signals which I am transmitting, and each of those signals can be in turn binary coded. So what it has done is to change the number of bits per symbol. If you want, you can also put per polarization, I will leave that one to you. So I have increased the number of bits per symbol from 1 bit to 2 bits per symbol. So what I have actually done is to increase the symbol rate while the bandwidth essentially remains the same. So this statement I am not going to prove here, you can look at your undergraduate textbooks for that, but essentially what we have done is to double up the spectral efficiency. So I have doubled the spectral efficiency. What is the problem with this approach? Well, the problem with this approach is that one, you have to switch the laser amplitude into 4 different levels. That requires you to generate multi-level signals in the electrical domain, because we can control the output power of the laser that is coming out of the modulator by adjusting the modulating signal u of t. So I have to have multi-level electrical signal, which is not easy to generate, and moreover I cannot continue this approach, okay, because the maximum amplitude or the maximum power that the link can withstand before link gets degraded, and I will tell you why it gets degraded later on, is actually usually fixed. Okay, so this is the maximum amplitude. So if I want to increase the spectral efficiency further, I will have to start making smaller and smaller intervals between the different symbols, right? But what I have so far shown you is only the signal points, but in a real system when you take these constellation points and actually look at what the received constellation will be, the received constellation is going to be looking something like this, and this looks, because all this red indicates that even when you transmit just say P3 or corresponding to S3, you will still have noise which will be distributed. So, the received constellation points will not exactly fall on P3, but they will be distributed around this one. Of course, this distribution will actually be two dimensional, but I am showing you only one dimensional to bring out that this is a one dimensional set. So, as I start making the interval between the symbols smaller and smaller, that is increase the number of amplitudes, I may increase the spectral efficiency, but I am actually going to be very prone to the noises that are present. So, noise actually kills this multi-level ASK system. It was tried, ASK systems with 4 levels were tried earlier, but this did not give the required performance that people were looking for. So, today we do not really use multi-level ASK alone, we actually combine ASK with what is called as PSK. So, what is PSK? Now, that is where we are going to get very interesting thing out there. Now, you have your carrier signal. In general, when you take a carrier signal, you can either specify the carrier signal by its amplitude. So, you will have signals which are actually transmitted in this form, right. So, this is the same thing whether you are looking at a wireless system or an optical system. Here omega naught comes from the laser. So, that is all the difference is. In the wireless or RF communication, this comes from an RF source or a crystal, whereas in this in optical communication, this comes from a laser. And then I have this plus theta, which is the phase that this laser would emit. Now, I have my signal u of t, and as we have seen earlier, one of the natural ways of converting an electrical signal into an optical signal is to go and modulate the phase of the optical carrier, right. So, I can go and modify the phase of the optical carrier, and in order to do that I will be using a phase modulator. What if you choose u of t to be that it will either produce a 0 volt or it would produce a V pi volt? When you send u of t with 0 volt, the output and input electric fields are in phase with respect to each other. So, therefore, you can think of this thing as 0 phase being transmitted. Okay, so, this is 0 phase being transmitted, whereas when u of t becomes equal to V pi, then the input and output are 180 degree out of phase with respect to each other, and taking this input as the reference, you are either being in phase with the output is either in phase with the input, or it is pi phase shifted with the output, and these two can be mathematically captured by allowing theta to go from 0 or pi. So, when you want to transmit a bit 0, you consider transmitting square root of 2 Es by t cos omega 0 t plus 0 phase, right. So, that is you set theta equal to 0, and when you want to transmit 1, you transmit this way. So, you have square root of 2 Es by t cos omega 0 t plus pi, which of course can be simplified because cos A plus B formula can be applied. Cos A plus B is cos A cos B minus sin A sin B, or plus sin A sin B I think, but sin of pi will anyway be equal to 0 and cos of pi will be minus. So, what you would be transmitting is minus square root of 2 Es by cos omega 0 t, and because cos omega 0 t plus 0 is essentially cos omega 0 t, these are the two carrier waveforms that you are going to transmit. But you can express these carrier waveforms by first defining say square root of 2 by t cos omega 0 t as this basis function phi 1 of t, and in terms of this basis function, 0 symbol, which let us say is S0 and S1, okay, S0 equals 0, S1 equals 1, these are the waveforms that correspond to the symbols. This would actually have a constellation point which is given by square root Es. This one will have a constellation point given by minus square root Es. Okay. Of course, in the way that we have written, I could have easily used the power here, but I am sticking with energy because this is kind of quite common in digital communication terminology. So, it might be better for us to get used to seeing these energies here. And if I were to ask you what is the energy of a laser over the time period, of course, it produces whatever the laser output power, but energy is basically the average photon number that you have times the energy of each photon, which is about h nu, and this is what is the relationship between energy, power and time, Okay, so you can clearly see that it is possible for us to actually relate energy and power and energy and the actual energy of the photon picture. So in terms of the photon picture also we can specify the energy. Okay, so but you notice here something, right? So I have square root Es and I have minus square root Es. In terms of the carrier, of course, I have square root of Es times phi 1 of t and minus square root of Es times phi 1 of t. Okay, in terms of the constellation, I have 2 points here. One corresponds to square root Es and the other corresponds to minus square root Es on phi 1 of t. This is the in phase component anyway, this is the quadrature component, and I am transmitting this constellation symbol. Okay, so far so good. We have transmitted binary phase shift keyed signal. This is called as binary PSK or binary phase shift keying, and we have transmitted this one. Now how do I receive? If you for a moment don't give it a deeper thought, you might think that I can simply put in a photodetector, have a load resistor RL, and then take out the voltage across that load resistor, and I should be all right. Right, that is what you would think. So this is at the receiver after it has come out from the fiber, right? So after it has come out from the fiber, the light is incident on the photodetector, and then we hope that the photodetector current IPH or the photo current would essentially allow us to distinguish between 0 and 1. Okay, what is the complex electric field that you are receiving here? The complex electric field that you receive here will be square root of 2 PS. I am now writing PS equals Cs by t e to the power j omega 0 t. When you transmit S0, that is for the symbol 0 you are transmitting this one. For the symbol S1, the electric field will be minus 2 square root of or minus under root of 2 PS e power j omega 0 t, right? And what would be the photocurrent when you transmit bit 0? The photocurrent will be R, where R is the responsivity, times the power, and power is basically S0t magnitude square. Therefore, this is equal to 2 RPS. Okay, the factor of 2 is not very important, you can just ignore that one. I just did not want to change the equations here, and therefore I have included here. But normally what we do is, when you have a cosine omega 0 t, there will also be half associated with that when you express this in terms of e power j omega 0 t. Therefore, this should have been written as square root of PS by 2. But our goal is not to really look at these multiplicative constants. They are just going to change the photocurrent levels here and there in terms of our mathematical model. But the basic idea here is that when you transmit S0 of t, then you would have received a power which is proportional to PS. Okay. Now the photocurrent when you transmit bit 1 will be R magnitude of S1 of t square, which would again be equal to 2 RPS in this case, because S1 of t magnitude square is the same of S0 of t magnitude square. Now we are in a fix. We get this photocurrent, but then both photocurrent values are the same, but my information is not in this intensity. My information is actually in the phase, whether I am transmitting a plus carrier or a minus carrier, that is I am transmitting phase 0 or pi, is what determines whether I have received a bit 0 or 1. But if by putting a simple photodetector I am not able to distinguish between the 0 phase signal and the pi phase signal, then this entire detection system is useless, right? Is there a way around for us to overcome this problem? Yes, there is a way around to overcome this problem, and that is a very clever idea. Okay, consider for example what would happen, when you have say some ES plus ELO. Now I have to apologize for using these symbols. In these symbols they actually stand for electric fields, not the energies. Okay, so let's say I have two lasers. One laser is at the transmitter, so I have the transmit laser diode, and then at the receiver I have another laser diode which I will call as the local oscillator. So I have a local oscillator, and what I do is I sum the two signals. Okay, I sum the two signals and then send each of those signals to a photodetector. Okay, right. So on this branch what I have here is the received signal Es of t, which of course could be either S0 of t or S1 of t depending on what you have transmitted. But here what I have is the local oscillator signal, which I have referred to as ELO of t. This is the electric field. So in terms of your powers, you can write this as say square root PLO e power j omega LO t. Okay. Now Es of t also we will rewrite this as square root of Ps e power j omega 0 t, or for E1 we will write it as minus square root Ps e power j omega 0 t. Okay. Now we are ready to look at what exactly is happening with this kind of a receiver. Now instead of using one photodetector, I am putting in two photodetectors, and for some reason I want to actually generate the sum signal, okay, which is going to go in this branch, and then on the other branch I want to generate the difference signal. Okay. How do I generate these two sum and difference signals? Well, this is what the device that we are going to use. This device, as you have seen, is a coupler. Of course, I should actually have the amplitude split ratio of 1 by root 2 with this. I am just not writing those 1 by root 2 terms here, but you understand the point, right? So I can send in electric field 1 in this port, another electric field in this port, that is two different light signals at the two different ports. The phase can be adjusted such that I am going to get E1 plus ELO in one branch. Of course, I should get by root 2 here, and then I get E1 minus E1 plus E2, E1 minus E2 by root 2. I can adjust this phase, instead of being 90 degrees, I can make this phase to be equal to 180 degrees. Okay, so that we have already seen with by choosing appropriately the value of kappa and LC, the length of the coupler, I can get whatever the phase I want, and this is what I have now. Now, what is the use of these two sum and difference signals? Consider this as the first photodetector and this is the second photodetector. What is the output of the first photodetector? We will call this as IPH1. This would be equal to, or this would be proportional to, Es plus ELO magnitude square. Remember, there will be a 1 by root 2 term, so you can also put that half term here. But if you expand this Es plus ELO, what you get is Es magnitude square plus ELO magnitude square. Okay, this is a simple this one, plus you will get 2 times real part of Es of t ELO conjugate of t. Okay. If you want, you can also put in this half. Okay, later on it might be useful for you. Then the output of the second one, as you can easily guess, will be actually equal to half Es magnitude square plus ELO magnitude square minus 2 real part of Es of t ELO conjugate of t. So except for the minus sign here, these two expressions are essentially same. Now what I am going to do is to actually connect these two and take the current, which I will call this as I with a subscript I. You will soon see I put a subscript of I, or if you want I can put in I in. Okay. So I will tell you what I in is. I in is actually equal to IPH1 minus IPH2. Now when you take the difference between these two, the constant terms, or at least the magnitude terms which are common to both photocurrents, will cancel with each other. Okay. And then you have 2 minus of minus 2 will become 4, but there is a half here, therefore that becomes 2 again. So what you get is 2 times real part of Es of t ELO conjugate of t. Okay. So I will write this as real part of. Now I am going to assume that I have transmitted some bit, okay, 0 or 1, and then look at the output of this one for the two different symbols. So initially, suppose I have transmitted S0 of t, which means that Es of t will be equal to S0 of t. So the output of the photodetector would be, or the not the photodetector, the output of this I, or the output photocurrent I in, will be actually equal to 2 times real part of square root Ps e power j omega 0 minus omega LO t. Is that correct? Because ELO we have already written it here, and conjugating, oh sorry, I should also multiply this one by PLO. So let me rewrite it in this case. So S0 will produce an output in which I can take 2, pull this PS and PLO out because they are essentially constants, at least I have not considered them to be time varying at this point, and then I have real part of e power j omega 0 minus omega LO t. Now what is the real part of exponential j omega 0 minus omega LO t? That is precisely cos omega 0 minus omega LO times t. You can show that when you transmit S1, right, then there will be a minus sign up there, and then what you get is minus 2 square root PS PLO, okay, and then you get cos omega 0 minus omega LO times t. Now the magic is that if somehow I take omega 0 equals omega LO, then this will be cos of 0t, which would actually be equal to 1. Similarly, this will also be equal to 1, and now you look at this. The current I in can be positive or negative. Please note that current can be positive or negative because we are actually looking at these differences. So, whatever the DC values that are there, so this is the actual received current here, let us say this is the actual received current here, and then the difference is what I am looking at, and this difference could be positive or negative depending on whether you have transmitted bit 0 or bit 1. Okay, so those possible combinations are there, but what is the magic here is that the current I in can actually switch between its signs to positive and negative. Now, if you were to put just a threshold of 0 here, I have not considered noises here, therefore, I am putting a threshold 0 here. If my current happens to be greater than 0, then I know that I have transmitted bit 0. If it is less than bit 0, then I know that I have transmitted bit 1 or I have received bit 1. So, in this way, right, what I have done is to actually receive the signals in the form of a coherent receiver or a coherent detection, in which I have also assumed that LO is equal to omega 0, or rather omega LO is equal to omega 0. If omega LO is not equal to omega 0, but it is stable, right, omega IF which is stable, then this is called as heterodyne communication system. This is called as homodyne communication system. So, what you have is coherent homodyne or coherent heterodyne. Usually we do not use this coherent heterodyne system, not really useful for us, or at least not really useful in this today's scenario, but this is what we are trying to achieve. But if the difference omega LO minus omega 0 is not equal to 0, but it is actually omega 0f and it is not very stable, then this omega 0f is called as the offset frequency or frequency offset, and this will actually impact our communication system, as we will see in the later modules. So, the lesson here is that a simple photodetector can never receive or directly measure the phase. What you have to do to measure the phase is to do a coherent receiver. It is also possible to use the incoming signal itself as a reference, but that is again, that is not something that is quite popular today. The popular thing today is the coherent receiver, in which two different electric fields are going to beat against each other. If the conditions are right, then the output could be either positive or negative, and by looking at the signs you can decide whether you transmitted bit 0 or bit 1. So, in the next module we will bring out the two systems, on off keying and the coherent BPSK system, and then show that BPSK systems are actually going to perform 3 dB better than on off keying systems for the same operating conditions. Thank you very much.